Digital and analog inputs. Push button, digital input. In this code, the forever block is used to repeatedly check the state of a push button connected to digital pin 2 on the microcontroller. The state of the push button is read and stored in the variable button state. If the push button is pressed, i.e., the state is high, the built-in LED on the microcontroller is turned on. If the push button is not pressed, i.e., the state is low, the built-in LED is turned off. This circuit requires one Arduino Uno, an LED, a push button, a 10K ohmega resistor, and a 220 ohms resistor. This schematic shows a circuit with an LED and a button connected to an Arduino Uno. A red LED D1 is connected in series with a 220 ohm resistor, R1, to digital pin 13. This resistor limits the current through the LED. A push button, S1, is connected between digital pin 2 and ground. A 10K ohm resistor, R2, is connected between digital pin 2 and 5V, acting as a pull-up resistor. This means that when the button is not pressed, pin 2 is held high by the resistor. When the button is pressed, it connects pin 2 to ground, making it low. This setup allows the Arduino to detect when the button is pressed and control the LED accordingly. To develop an electronic circuit, please follow the steps outlined below. Identify the push button, LED, 2 resistors, and wires connected to the Arduino and the electronic circuit. Bring an Arduino Uno and breadboard from the components storage box to the workspace. Connect breadboard power, plus, and ground rails to Arduino 5V and ground, GND, respectively, by clicking to create wires. Extend power and ground rails to their respective buses on the opposite edge of the breadboard by connecting a red wire between both power buses and a black wire between both ground buses. Plug the LED into 2 different breadboard rows so that the cathode, negative, shorter leg connects to one leg of a resistor. Anywhere from 100 to 1K ohms is fine. Connect other resistor leg to ground. Wire up the LED anode, positive, longer leg, to Arduino pin 13. Bring a push button from the component storage box to the center of your breadboard and place it across the center column break so that its legs are plugged into 4 different breadboard rows. Click to create a wire connecting one button leg to power. Connect the diagonally opposite leg to Arduino digital pin 2. Create and position a high-value resistor, such as 10K, between that same button leg and ground. Add a multimeter component to the workspace and wire it up to Arduino pin 2 and ground. Upload the code and click to press/hold the push button to observe the digital signal being picked up by pin 2. The C++ code reads the state of a push button connected to digital pin 2 and controls the built-in LED accordingly. In setup, pin 2 is configured as an input and the built-in LED pin as an output. The loop function continuously reads the state of pin 2 using digital read and stores it in the button state variable. If button state is high, meaning the button is pressed, the built-in LED is turned on using digital write, LED_built-in high. Otherwise, if the button is not pressed, the LED is turned off using digital write, LED_built-in low. A small delay is included for simulation performance. Potentiometer, analog input. The exercise explains how to use a potentiometer as an analog input with an Arduino. The potentiometer is a type of rotating variable resistor. The lesson describes how to connect the circuit using a breadboard and Arduino code to control a single LED. The lesson introduces analog input, which senses a gradually changing electrical signal from turning the potentiometer and converts it to a range of numbers from 0 to 1023. The lesson also provides instructions for building the circuit with an Arduino Uno board, USB cable, solderless breadboard, LED, resistor, potentiometer, and breadboard wires. This circuit requires one Arduino Uno, an LED, a 250K ohmega potentiometer, and a 220 ohms resistor. This schematic depicts an Arduino Uno controlling an LED and reading an analog input from a potentiometer. A red LED D1 is connected to digital pin 13 through a 220 ohm resistor, R1, which limits the current to protect the LED. The potentiometer, RPOT1, is connected as a voltage divider. One end is connected to 5V, U1_5V, the other to ground, U1_GND, and the wiper, the adjustable middle terminal, is connected to analog pin A0. This setup allows the Arduino to read the position of the potentiometer's knob as an analog value between 0 and 1023, corresponding to the voltage between 0V and 5V. To develop an electronic circuit, please follow the steps outlined below. Identify the potentiometer, LED, resistor, and wires connected to the Arduino in the electronic circuit. Bring an Arduino Uno and breadboard from the component storage box to the workspace. Connect breadboard power, plus, and ground rails to Arduino 5V and ground G&D, respectively, by clicking to create wires. Extend power and ground rails to their respective buses on the opposite edge of the breadboard. Optional for this circuit, but good common practice. Plug the LED into two different breadboard rows so that the cathode negative, shorter leg connects to one leg of a resistor. Anywhere from 100 to 1K ohms is fine. Connect other resistor leg to ground. Wire up the LED anode, positive, longer leg, to Arduino pin 13. Bring a potentiometer from the component storage box to your breadboard so its legs plug into 3 different rows. Click to create a wire connecting one outer potentiometer leg to power. Connect the center leg to Arduino analog pin A0. Create a wire connecting the other outer leg to ground. The C++ code reads an analog value from pin A0, presumably connected to a potentiometer, and uses that value to control the blinking speed of the built-in LED. In setup, pin A0 is configured as an input and the built-in LED pin as an output. In loop, the code reads the analog value from A0 using analog read and stores it in sensor value. The LED is then turned on, followed by a delay of sensor value milliseconds. The LED is then turned off, followed by another delay of sensor value milliseconds. This makes the blinking speed of the LED directly proportional to the analog value read from the potentiometer. PR motion sensor, digital input. You can view the electronic circuit here. This circuit requires one Arduino Uno, an LED, a PIR sensor, and a 220 ohms resistor. This schematic connects an LED and a PR, passive infrared, motion sensor to an Arduino Uno. A red LED D1 is wired to digital pin 13 through a 220 ohm resistor, R1, to limit current. The PIR sensor, PR1, has 3 connections. VCC connected to 5V, U1_5V, GND connected to ground, U1_GND, and out connected to digital pin 2 on the Arduino. The PIR sensor outputs a high signal on its out pin when motion is detected and a low signal when no motion is detected. The Arduino can then read this signal on pin 2 to determine if motion has been sensed and control the LED accordingly. This exercise is to sense movement in a room with a PR motion sensor and Arduino board. This C++ code reads the state of a digital pin, pin 2, likely connected to a PR motion sensor, and controls the built-in LED and serial output accordingly. The setup function configures pin 2 as an input and the built-in LED pin as an output, also initializing serial communication at 9600 baud. The loop function continuously reads the state of pin 2 using digital read and stores it in sensor state. If sensor state is high, motion detected, the built-in LED is turned on and sensor activated, is printed to the serial monitor. If sensor state is low, no motion, the LED is turned off. A short delay is added for simulation stability. Photoresistor, analog input. You can view the electronic circuit here. This circuit requires one Arduino Uno, an LED, a photoresistor, a 4.7K ohms resistor, and a 220 ohms resistor. The schematic shows a circuit for reading analog data from a photoresistor connected to an Arduino Uno. The photoresistor, R3, is connected between 5V, U1_5V, and analog input A0. The other end of the photoresistor is connected to ground, U1_GND. As the light intensity changes, the resistance of the photoresistor changes, altering the voltage on the analog input pin. The Arduino can read this analog voltage and use it to determine the ambient light level. Additionally, a red LED D1, is connected to digital pin 9 through a 220 ohm resistor, R1, to provide visual output or indication. This simulation is about reading the value of a photoresistor, which is a light-sensitive type of variable resistor, using Arduino's analog input. It's also called an LDR, light-dependent resistor. This C++ code reads the analog value from a photoresistor connected to analog pin A0 and uses it to control the brightness of an LED connected to digital pin 9. In setup, pin A0 is configured as an input, serial communication is initialized, and pin 9 is configured as an output. In loop, the code reads the analog value from A0 using analog read, stores it in sensor value, and prints it to the serial monitor. The map function then linearly scales the sensor value, which ranges from 0 to 1023, to a range of 0 to 255, suitable for analog write. This scale value is then used to set the LED brightness using analog write 9. A 100 millisecond delay is added at the end of the loop. Temperature sensor, analog input. You can view the electronic circuit here. This circuit requires one Arduino Uno, 3 LEDs, a temperature sensor, and 3 220 ohms resistor. This schematic shows an Arduino Uno connected to 3 LEDs and a temperature sensor. The temperature sensor, likely a thermistor, is connected to analog input A0. The LEDs, D1, D2, and D3, are each connected in series with a 220 ohm resistor, R1, R2, and R3, and a digital pin on the Arduino, D2, D3, and D4, respectively. This setup allows the Arduino to read the temperature from the sensor and control the LEDs to indicate different temperature ranges. This exercise is about using a temperature sensor to measure temperature and register the output with 3 LEDs. This C++ code reads temperature from an analog sensor connected to pin A0 and controls 3 LEDs connected to pins 2, 3, and 4, based on temperature ranges relative to a baseline temperature of 40 degrees Celsius. In setup, pin A0 is set as input, the LEDs as outputs, and serial communication is initialized. In loop, the raw analog reading is converted to Celsius using a map function with an offset and scaling factor, then converted to Fahrenheit. The Celsius and Fahrenheit values are printed to the serial monitor. Based on the Celsius temperature relative to the baseline temp, different combinations of LEDs are turned on. Below the baseline, all LEDs are off. Within 0 to 10 degrees Celsius above, LED 2 is on. Within 10 to 20 degrees Celsius above, LEDs 2 and 3 are on. Within 20 to 30 degrees Celsius above, all 3 LEDs are on. And above 30 degrees Celsius above, all 3 LEDs remain on. Ultrasonic distance sensor. You can view the electronic circuit here. This circuit requires one Arduino Uno, 3 LEDs, an ultrasonic distance sensor, and 3 220 ohms resistor. This schematic shows an Arduino Uno connected to an ultrasonic sensor and 3 LEDs. This circuit requires the ultrasonic sensor Uno, labeled 3 LEDs, SR04, an ultrasonic distance sensor, and 3 220 ohms resistor. TRIG, Echo, and GND VCC is connected to 5V, U1_5V, TRIG to digital pin 12 D12, and Echo to digital pin 11 D11. The 3 LEDs, D1, D2, and D3, are each connected in series with a 220 ohm resistor, R1, R2, and R3, to digital pins 2, 3, and 4, respectively. All LEDs share a common ground connection, U1_GND. This setup allows the Arduino to use the ultrasonic sensor to measure distance and control the LEDs to indicate different distance ranges. This exercise is about measuring distances with an ultrasonic rangefinder, distance sensor, and Arduino's digital input. To develop an electronic circuit, please follow the steps outlined below. Bring an Arduino Uno and breadboard from the component storage box to the workspace. Connect the 5-volt and ground pins on the Arduino to the power, plus, and ground rails on the breadboard with wires. Bring 3 LEDs on the breadboard in row E, spaced 2 breadboard sockets apart. Use a 220 ohm resistor to connect each LED's cathode, left leg, to the ground rail, black, of the breadboard. Connect the LED anodes, right legs, to digital pins 4, 3, and 2 on the Arduino. In the circuits editor, find the ultrasonic rangefinder in the components storage box. Place the sensor on the breadboard to the left of the LEDs in row E. Wire up the sensor, so the 5V pin connects to the 5V voltage rail, the GND pin connects to the ground rail, the SIG or TRIG pin to Arduino pin 7, and if using the 4-pin flavor, the Echo pin connects to Arduino pin. This C++ code uses an ultrasonic sensor connected to digital pins 7 and 6 for trigger and echo, respectively, to measure distance and control 3 LEDs connected to pins 2, 3, and 4. The read ultrasonic distance function sends a pulse to the sensor and measures the time it takes for the echo to return, converting this time to a distance in microseconds. In loop, this distance is converted to centimeters and inches, printed to the serial monitor, and then compared to a distance threshold 350 centimeters. Based on the distance, different combinations of LEDs are turned on.